Good afternoon, everyone. Um, so I will take you through the manual first. Then we will see that some basics, what basics about what is running behind our simulation. So up to this theory part, we will see. After that, we will launch Abaqus and do it step by step. Okay. So our objective is to do orthogonal machining. So to study the cutting edge radius in ultra precision machining of ductile materials. Okay. So very important thing here is in the theory part. This is a material model which we are going to use. So JC material model we are going to use it. So how the material is going to deform under the when we push the tool to the workpiece, how the material is going to deform. That is dictated by this particular material model. And there is one more model we will see, which is nothing but damage model. So our chip is forming, okay, from the workpiece. We are cutting the material and removing the unwanted material in the form of chip. So how that removal is taking place? That removal is taking place because of the damage. So we will be using JC damage for that. And again, we will do study one more technique called arbitrary oil agent technique. So all these three things are already embedded into our Abaqus. So we don't have to write any coding or stuff. So we just go and pick up and input some values and we do the simulation. But before doing that, we should understand what are these three things. Okay. So coming to this machining part, we have strain rates in the order of 10 to the power 4 to 10 to the power 6 per second. Okay. So if we take tensile testing, the strain rates are in the order of 10 to the power minus 4. So if that the case, we will have only strain hardening effect. Okay, say for example, you can see the stress strain curve. We can have elastic part and then we will have plastic part, where the plastic part is described by k epsilon power n. So the same thing is here. Okay, this particular first term is there in JC material model, which talks about strain hardening. Okay, so in tensile testing, we will be having strain hardening case. But what is happening to our machining part? Okay, in machining part, we are deforming the material very high strain rate and it can go up to 10 to the power 6 per second. So because of this, strain rate hardening also comes into play. So our material model should be in a position to take care of this strain hardening part also. So even also at this particular high strain rate, temperatures are being generated and the temperature softening is also taking place. So your material model should be in a position to take care of your temperature softening also. So there are many material models are out there which can take care of this strain rate hardening and thermal softening effect. But we will be using the famous Johnson Cook material model or constitutive model because of its easy of adaptability to computer simulation. Actually, this is already inbuilt in your Abaqus. There are many more simple failure models are there which are not suitable for machining. This is a highly non-linear problem, so we have to use JC model only. Else we have to go for coding. So we don't want to go for coding. So we will just use the inbuilt JC model for our simulation. Okay. So our JC model is something like this. So this is the flow stress. Flow stress is equal to function of strain. That is, this part is strain hardening. So this particular part is strain rate hardening. This is thermal softening. Okay. So like these are the constants which we are going to input to this. Say for example, A, B, and N value. So this is a plastic part of strain. Don't think this is a some constant. So it is just strain, but we are ignoring the elastic part. We are just only considering the plastic part. So most of the metal forming problems or machining problems, we don't take care, we do ignore the elastic part. It is not much significant. So we ignore the elastic part. So when we take only plastic part. So your strain is nothing but only plastic part. Okay. So this is your initial yield. Then this is K epsilon power n, same strain hardening component. Then we have one more thing like C multiplied by strain rate. Okay, so what is the strain rate star? You can see it here. Okay, so which is the ratio of plastic strain rate divided by reference strain rate. So this is like we can't find these constants A, B, C values at machining at very high strain rate. We can't capture these values. So what we do is we take testing like Oppinsken bar test or any other test. We will take it. Possibly it will go up to strain rate up to 10 to the power 4. Then we will see what is the A value, B value, and C value, and there is separate procedure for that. Then accordingly, we have to give the strain rate value. Say for example, if we are doing 10 to the power of 4 strain rate, and at that strain rate we are calculating or estimating this A, B, and C value. Then we have to give this one as 10 to the power of 4. But in our experiment, uh, the strain reference strain is nothing but 1, and accordingly values A, B, and C values are extrapolated. Okay, extrapolated up to 10 to the power of 6 strain rate. So this is what we are going to use it. So these constants we have to give it A, B, N, C. We have to give it again. This M we have to give it. So what is M? T power M. You can see T minus T room divided by T melt minus T room. These two temperatures we will give, T melt and T room. This temperature we will give. So totally 1, 2, and 3. 4, 5, 6 constants we have to give into that. So this is already available in the literature, which I had given in our manual below. So you don't have to worry about. Just um, understand the material model which we are using. So even if you are going for some other material model, it should be function of strain rate, and temperature. Okay. So this is very important. Okay. So rest of the things you can go through it. Okay, so what is happening? Okay, once we give material model, once we start deforming the material, what is going to happen to our mesh? Okay, so I hope you might have exposed to finite element method. So in finite element method, what we do is we create meshes. Okay, we create meshes, and then in the meshes we will apply our physics. So whatever physics we will apply and boundary conditions we will apply. So then the material will start moving. Okay, so for example, our chip is will start moving. So what is going to happen when we do that? So in machining or metal forming, the material movement is highly non-linear. It is not linear, and because of this, we will face some issues. Okay, so the way FEA works is the element, which is finite element method, whatever element is there, it should not deform too much. If it deforms too much, then it can't handle it. So what we have to do is we have to remesh the remesh the mesh again and again. We have to remesh it and again do the problem like that. So this is a problem with this large deformation problems. So what how we are going to handle that? That is very important. Say for example, there are two ways we can formulate our physics. Okay, so our physics could be like isotropic. So this is our physics basically. So simply, if it is just strain hardening, then this is our physics. This is actually this is how the material is deformed. Okay. So what is happening at the machining? So mesh is moving. So because of that deformation, distortion, mesh distortion issues comes into play. So but if you do simulate fluid problems, we don't face mesh distortion issues, but we will have boundary. We have difficulty in tracking the boundary. So in I can say in control volume and control mass you might have studied. Simply I have to say there are two approaches. One is control volume approach, which we use it for fluids. Another one is control mass approach, which we use it for solid mechanics problem. So same thing is here mentioned here. Say for example, Eulerian is yeah, I mentioned the Eulerian is advantages for handling large deformation problems. So Eulerian is nothing but your control mass approach. Lagrangian is nothing but your control volume approach. So both as it's the both advantage and disadvantage. Okay. So basically, we are going to use a hybrid of both Eulerian mesh and Lagrangian mesh. So it is like arbitrarily we will solve the problem in Eulerian frame, then we will map it to the Lagrangian frame. Somehow how we map is arbitrarily we are mapping. So we are not going to see the techniques. So it is very complex. So we are not going to see the technique, but simply be aware that in order to avoid mesh distortion issues, we will be using ALE technique. Okay, so we just go into Abaqus and choose this ALE technique. Okay, so but the advanced version is like coupled Eulerian technique is there. So that is available only in 3D. So we are not going to do coupled Euler Lagrangian. So we will do all our problems in 2D itself using arbitrary Euler Lagrangian technique. So you make sure you understand this. There is this technique is important to avoid your mesh distortion issues to some extent. Not completely, we can't avoid it. If we have to avoid the mesh distortion issue completely, we have to go for coupled Euler Lagrangian. But we are not going to do that. Okay, for this tutorial. So after that, one important thing is damage model. So this damage model is the one which differentiates our machining from our metal forming problem. So for our metal forming problem, mostly we use JC material model and ALE or CLE technique. But this damage is very important because we are damaging the material and removing the unwanted material in the form of chips. So how that damage is happening? So that is dictated by your many laws. Many laws are there, but in machining, obviously, as I said in the previous case, we do have strain rate effect and temperature effect. So those strain rate and temperature effect should be part of this damage model. So what is this is out of many damage models. Again, we do have JC damage model. Okay, so which is nothing but the below equation. So your failure strain. So at what particular strain the material is going to failure. So say your failure will your stain will start accumulating when we do machining or when we start staining it, the stain will keep on accumulating. So after it reaches some critical strain, it is going to fail. Okay, so what is that failure state? That is given by your Johnson Cook damage model, which is nothing but function of your stress triaxicity, and again it is a function of strain rate, and this is nothing but normalized strain rate they call it. Okay, then again same thing, homologous temperature or thermal softening, the same effect whatever we saw here, the same T and strain rate here, same we will have here. But only difference is this first step. So here we had a material model, we have strain hardening, but we have here stress triaxility. Okay, so this stress triaxility is common for most of the damage model. So it is very important to for you to understand this also. Okay, so what is stress triaxility? So which stress triaxility is nothing but ratio of hydrostatic pressure to von Mises equivalent stress. Okay, so in your advanced strength of materials, in mechanical behavior of materials, you could have studied about deviatoric stress and hydrostatic stress. Okay, so that is this one. Okay, so average stress. So this one is causing your material to change in the size, not shape. Okay, so your deviatoric stress will make the material to deform. It makes the shape change. Okay, so I hope you understand that one. So this is one Mises equivalent stress. Okay, so equivalent means that is in 3D. Okay, so already you might have already you have studied about von Mises failure theory. Von Mises design in a design of machine elements, you could have studied about von Mises theory. So same thing which we are using it. So this particular term is very important. So otherwise, these things are already calculated by our software. So we don't have to worry about this. What is this stress diactivity? All those things it will be calculated by computer. But what we have to do is we have to input these material constants: D1, D2, D3, D4, D5. So these five constants we have to give it to our computer. And sorry, this also we have to give it. Okay. So six constants we have to give it to your computer. Based upon that, it will calculate what is the current plastic strain. So once that particular plastic strain crosses this particular failure strain, then your material is going to get damaged. Okay. So your load carrying capacity of your element is going to decrease. Okay. So that is how things are working. So very important thing what I want to highlight here is um, we have to mention evaluation criteria. Say for example, once we have this ultimate tensile point in your 1D case, the load carrying capacity goes down. Say for the curve is at the top and it will go down up to fracture. So how it is going down? Why it is going down? It is because of it is a ductile material. Okay, in your tensile stress, after your UTS point, your curve will go down. Why? Your load carrying capacity is decreasing. So because of ductility, it is decreasing. So we have to mention what is this evaluation criteria. If you are not getting any results, suppose there are no errors are coming, but end of the thing, if you are not getting any results properly, then that will be because of your something you might have given wrong numbers in the evaluation criteria. So this I will tell you when we are doing our Abaqus simulation. Okay, so these three theories are very important: JC material model and JC failure or damage model, and how we are handling our large deformation problem. So these three things are very important before we go into our Abaqus. Okay, so once we start our Abaqus, we will do this whatever values I have given, the same thing we will do it, and then it will be very straightforward answer, and we will get this one. Okay, so finally what you are supposed to get is this simulation like this. So I will show video by end of this tutorial. So for example, your tool will be initially at this place and it will keep on going. So here the material failure is happening. That's why here chips are forming. Okay. So here you can see it here this particular place, your failure stain will be reached. So once this failure stain is reached, this particular element will be deleted. So actually deleting the element is not the right way to do it, but it reduces the load carrying capacity. However, we are going ahead with that. Okay, so with the student version, you may not get like this. I will tell you why. I will while doing the simulation online. I will tell you what is the problem. Okay, so but fine. I did this with very refined mesh, more than 1,000 nodes. But if you are using standard version, we can't have more than 1,000 nodes. So what I did is I modified. Uh, I modified these things. I modified this dimension and I did some changes such a way that you can have only less than 1,000 nodes so that you can do our simulation in your Abaqus, student version. So I will take you through that. At that time, I will tell you what is how we are going to get our answers in student version. Okay. Say okay. Any doubts till now? Any doubts? So if you have any doubts, just stop me. Okay. So let me launch my Abaqus. So you click this first option with standard or explicit model. So you do this one. Okay. So this is pretty much if you are not this is the first time if you are using Abaqus, still you can manage it. I will take you through step by step, but you have already gone through SolidWorks or Creo. So these are like pre-processing stuff very easily we can do it. Okay. So any doubts you can ask me and stop me. So let me okay. Let me save this model. Okay, first of all, you first save this. So save it in particular folder, because whatever this operation, when we start doing operation here, many files will be created. So that will be stored in your default folder, which is nothing but you can say if you say save as, it will go to your temp C temp. It will go. Yeah, let me show it. Set working directory. Okay. So if you see that your default working directory is ctemp, so whatever file you save, or even if you run the simulation, all the files will go and save in temp. So first time when you are doing that, this will not create any issue. But second time if you do it, then the files will be overwritten on this same folder. Then it will create a lot of issues. So we don't want to do that happen. So before setting my work directory, let me save this file in a proper place. So in TA work, I'm saying simulation lab class, and obviously you have batch 6. So in batch 6 folder, I'm giving the file name as try and save as okay. So you can go and see it here. Okay, TA work simulation lab class batch 6. So there are one more file is created. Okay, so these two files are very important. When we do simulation, here some other files will also come into play. So for that to happen, you do the set working directory, change it to the folder which we have created, TA work, simulation lab class, batch 6, and click OK and say OK. So now whatever files we are creating, that will be saved in this. Say for example, when we are doing simulation, some temporary files will be created that will also store here. So this is very important step. If you don't do this step at the first place, then you might face some problems or errors which you can't easily understand. Okay, so you do this procedure first. Okay, so now I am done. So let me take you through this what we are going to do. Okay, for example, this is a model tree. Okay, so in the model tree you can go and create whatever commands you want, but I will be mostly using this module one, which talks about step by step procedure how we have to do it. Say for example, in module part one, we will create our parts. Say for example, workpiece we will create, tool we will create, then we will go to property, then we will give a material property, aluminum material property to our workpiece. So likewise, then we will assemble both work and tool in this particular step. Okay, so then we will do this final step. This is where you do choose your physics. So basically we will go in order. Okay, so when we change property, then the here tools will change. Okay, so like once you created your step, you have to create the interaction part. Say for example, your coefficient of friction between the work and tool, we will mention it here. Then finally you have to do boundary conditions. Okay, so boundary conditions we have to give whether what are the loads you are giving or what is the cutting velocity you are giving. All those stuff we will give it here, and then we finally mesh the workpiece. Okay, then we don't do optimization, we will straight away go to job. Here we just create a job and we ask the solver to solve it for us. Okay, this is nothing, this is very simple, we are not going to do much on this one. Okay, so visualization is nothing but seeing your results. Okay, so whole idea is even if you don't know Abaqus, it is very straightforward way. Okay, you can go step by step. Okay, say for example, here part, I click it, I can create part here. You go over here and over the pointer, then it shows create part. Okay, so here I can go and create a part, or I can go to model tree and right click the part and create. This can also I can do it. Okay, so here you can get a overall picture of what is going on. Okay, so for example, under loads or boundary condition, nothing is there. Okay, once we create here, loads, once we create our boundary conditions, you will see some numbers, you will see some other changes here. Okay, so sometimes I do use this one, sometimes I do use this one, so it is your convenience only. Okay, so let's create our 2D case problem, our workpiece and tool. Okay, so what we are going to do is, um, we will create a deformable 2D body as a workpiece. Okay, so I have not mentioned this as a workpiece. 2D deformable body is nothing but a workpiece, but I am not going to do it by 4 mm by 2 mm. I will do it by 2 mm by 1 mm. So because we have to reduce the domain of workpiece so that we will have a better mesh that is lower than 1000 nodes. You can have it in your student version. So if you go for this high level, then we will get much more coarser mesh. That way I want to avoid it. So I will be modeling 2 mm by 1 mm as my workpiece. Then I have to model the work tool as a rigid body. Okay, so obviously your tool is not a rigid body, it is a deformable body only, but for simplicity's sake and to avoid the number of nodes, so on this rigid body, so I don't want any discretization on the tool part. So if I discretize my tool, then again it will take some number of nodes, then this again it will become much more coarse, so I will not get the answer properly. So I kept it like simply rigid body for your tool with a 10-degree rake angle, clearance of 2 degree, and obviously edge radius I initially mentioned it as 100 microns, but I will demonstrate you with 60 microns. Okay, so you guys will be doing with the different microns. Say for example 30, 45, 60. You guys 60 or 70 you can keep it, or better keep below 60. Okay, so I will tell you by end of the class who has to do with how many edge radius. So I will tell at the end of the class. Okay. So let's go and create this part generation. First, we will create our tool with 2 mm by 1 mm. Okay. So go here. You can go here and create part. So change this one as work. So I'm not going to do 3D part. I'm going to do 2D part. Okay. So obviously it is deformable body, not rigid body, and this number we are going to change it. Okay, so this is like a graph size. So suppose if you give this as a 200 and we are going to give the dimensions in mm. Okay, so if we do that, then if somehow the screen resets, then we have to go and find where is my workpiece. So we don't want to do that, so we have to give graph size. Okay, so it is like 0.01 because I'm going to do it with 1 mm. So this particular setting will be okay for me. Okay, so continue. Okay, now you click here. Sorry, I'm going fast. You go here, rectangle is there. You click here and click somewhere. and drag it and click another point. Okay. Now press escape. So I got a rectangular workpiece in 2D, but what is the size of it? I'm not sure. I have to change the dimension of this one. Okay. So for example, there is something called here dimension. Okay, add dimension. It is not simply adding dimension. Say for example, this is of some other value. If now I add dimension, I can change this particular length. Okay, let me click this one, click this and drag it and click this. Okay. So whatever length I defaultly created is nothing but your 3 mm. You can see it right. 0.003 is nothing but 3 mm. So, but I want it like 2 mm. Okay. So this is 2 e power minus 3. So this is 2 mm I want. Enter it. Now it has changed. Initially it was 3 mm something. Now it has changed to 2 mm. Likewise, you click this and go here. And I want this one as 1 mm. Okay. Done. So some other softwares won't allow like this, but in Abaqus it is allowed like this. This is how you create a particular part with particular dimension. Okay, I'm done with this one. So say done. Okay, so now you can see there is workpiece created here. So in the model tree you can see it here. Initially there was nothing. Now I can have something called work. Okay, so I'm going to create one more thing which is called a spot. Either I can go here or right click this part and show make this as a create. Okay. So now I'm going to make tool. Okay. So tool is not a deformable body. I want to model it as a rigid body and keep the approximate as point not one itself enough. Continue. Okay. So go to the then again. What is the size of the tool which we have to create? That is very important. So you can go by any size, but uh, any size you go, it is not going to affect your computational accuracy, but your chip has to prove. So you make sure what is the depth of cut you are giving or uncut chip thickness. What you uncut chip thickness based upon that, you can change the tool size. For example, you better you keep this dimension what I am giving right now. So, okay. So 0.5 mm by 0.5 mm rectangle we will draw first. Then we will give our rake angle. Okay. So 0.5 mm by 0.5 mm works fine. You can go for 1 mm by 1 mm also. It's not a big. It will not make any difference. Okay. So I want 0.5 mm. Okay. Let me zoom it. F2. I can move it like this. Okay. So this is my tool. Okay. So this is my cutting place. What I have to do is here I have to create my rake angle, and here I have to create a line such that it will have my clearance angle. Okay. So let me click line. Click this particular point. Click somewhere arbitrary, press yes. So now I have to dimension this one as rake. Okay, what is my rake? Rake is 10 degree, clearance is 2 degree. You will come to the dimension part later. Let me draw one more line here. Clearance. Okay. So don't click any point here, it will get auto constraint. So keep it somewhere away. Okay. So before we can dimension it better now itself, we can dimension it so that this is 10 and clearance is 2 degree. So what I did is you went there, click the first line, click the second line, and somewhere in the middle, click it. Okay. So 2 is your clearance angle. Okay. So I gave this one. You better you finish this one. Then we have to give edge radius to our tool. So now the tool is very sharp. Okay. Very sharp. This is the ideal case, but no tool is sharp, but relatively it can be considered sharp. So here we have to give edge radius. I'm going to give 60 microns as my edge radius. So how to create that? So better go here and create a circle. Okay, create circle somewhere outside. Okay, press escape and dimension this one as 60 microns. Click this, and do like this. 60 e power minus 6. Okay, this is 60 microns. I'm not sure whether. Okay, once again, let me do it for radius. So keep it like this so that we will dimension this point to this point as 60 microns. So like this, it has to go, not straight way or something. Yeah, 60 e power minus 6. Yeah, now it has reached. Okay, this is 60 microns. So what I'm going to do is I'm going to move the tool and fix it here, make it tangent to this newly created line, so that I will get a smoothly varying edge radius. Okay, so let me move this one. Okay, so in order to move this and make it tangent to these two lines, what I have to do is I have to add constraint. Okay, add constraint and tangent. Okay, this and this. If you click it, you can see it like this particular one moved according to the circle. I don't want that to happen. So I want this circle to move to this place. So let me do Control Z. Okay. You can fix these lines. Okay. So that this will move here. So let me fix it. Okay. Fix this line and shift this line. Okay. Now these lines are fixed. So, and again, these lines are constant to these lines. So this setup won't move. Okay. So now this will move to this place. Okay. So let me choose tangent, click this one and click this one. See, now it has moved. So the other case also fine, but I'm comfortable with this one. That's why I'm doing like that. Okay. Again, click tangent, click this one, and carefully choose the second line. So you can see it here. Now it has become tangent. Okay, tangent to the new line. So all I have to do is trimming of unnecessary parts. So my part is this one. It goes like this, goes edge radius, then it goes like this and goes back like this. So I will do the trimming part. Okay. So this is the trimming part, auto trim. So you click this one and go over here, it will highlight the unwanted one. So these are unwanted one. So I'm removing this, I'm removing this. Zoom it, this is also unwanted, this is also unwanted. This is the sharp point we don't want, unwanted, unwanted. So the from tool it is going like this. So this is unwanted and this is unwanted. Now you can see clearly how nicely you are having the edge radius. Okay. So this has to be closed one, else you won't get it. So make sure you do it this one properly. Say into done. Yeah, everything is fine. So I have done with my tool also. Okay. So you can see in under parts we'll have work and tool. When you can go here under part model one. So our model one is this one. So here we can choose our workpiece and tool. So this is how we do it. Okay. So next step is to create property, material property. Okay. So this is your create material. So let me name it as ALU. Okay. So go to your PDF. All the data are given. So these are taken from our reference paper. So you have to give density first. You have to give everything. See in Abaqus, it won't ask for units. Okay, whether you are giving in mm or meter, that you have to take care of it. So if you are giving in you have to interpret the results also accordingly. Okay, say for example, I don't want that interpretation. That's why I gave 4 as 4 e power minus 3. So I'm doing in terms of meter only. So likewise, here also I'm taking kg per meter cube. So I don't have to change anything. 2700 is fine. So let me give density, general density. So 2700. So this is kg per meter cube or cube. That are ton per ton per meter cube or something or centimeter cube. That you have to keep it in mind. Okay. So I'm giving everything in simple SI units. Okay. So I gave density. Then what I have to give is Young's modulus. I have to give elastic property. So you go mechanical, elastic, elastic. Okay. So what is your Young's modulus? 650 gigapascal. Giga means e power 9. Okay. So Poisson ratio is 0.2. Okay. So obviously in calculation it don't take this one, but this is necessary to see to at the start we have to know with some guessing of plastic strain, so that are yielding. So from this one, the computer will start guessing. Okay, what is the strain which we have to give it? We have to start with it like that. Okay, so that is different. But elastic part we have to give. That is very important. Okay, so then Poisson ratio I give only plastic properties I have to give. Okay, so JC material property and damage property we will give it here. So go to mechanical, material plasticity, go to plastic. Okay, so your material is not isotopic, your material is Johnson Cook material. So click that one. So now it is showing the different constants which you have to give. A, B, N, M, melting temperature, transition temperature. Okay. So what is your A value? A value is 324 e power 6. It is megapascal. 324 e power 6. What is B? 114 e power 6. 114 e power 6. What is your N value? 0.42. 0.42. What is your M value? 1.34. So in this study, we are not going to consider the temperature effect. So I'm not going to fill any numbers on this one. Okay. So I'm leaving this one blank so that you will take it as 0. Okay. So one more thing is a strain rate components I have not given. What is C value? I have not given. For that, you have to go to sub option. This is very important. Sub option and rate dependent you have to give. Okay. And then in the hardening, you can see Johnson Cook hardening. Okay. So which gives constants. It is asking for constant C and epsilon dot 0. Okay, epsilon dot value. Okay, C is nothing but I already mentioned here. C is nothing but 0.002. So epsilon dot is generally 1 unless otherwise it is specified as some other number. So click this and OK. So we set the JC material parameter. We already set it. Only thing is JC failure model I have to do. See, once you define plasticity, damage you have to mention it. So JC model is nothing but ductile failure only. Okay. So damage for ductile materials. Go here. The second option is your Johnson Cook damage. Click that one. Now you can see it is asking for D1, D2, D3 up to D5. So these things we don't have to do. What is D1? Already I have given here minus 0.77, D2 1.45, D3 minus 0.47, D4 is 0, D6 is 1.6. Okay, so right now we don't have to give reference strain rate here. It will work fine. We go to sub option. This is very important. Let's see whether it will create any issues. If it is not creating any issues, we will leave it. If it creates any issues, we will give reference rate as strain rate as 1. Okay. So like what we had defined in the JC material model. So only thing is sub option. This is very important. Damage evolution. Okay. So whatever data you fill that tells the computer when failure is starting, but actual degradation of the material will start only if you give damage evolution. Okay. So you have to tell damage evolution in terms of displacement of energy or fracture energy. Yeah, from fracture mechanics concept, what is the fracture energy of your aluminum? You have to give it, or you have to give it in terms of displacement. Okay, this is like proxy for your strain. Okay, so there are reasons why instead of giving strain, they are giving displacement. Okay, so we don't want to do that, but this number is very important. You make sure you give this number with the setting, else you won't get the answers. Okay, so failure 1 e power minus 5 you give it. Okay, so I will tell you why I am giving. Okay, so this is what I'm going to do is I'm going to give my mesh. Okay, my mesh is 5 e power minus 5. So my displacement or failure should be less than 5 e power minus 5. Then only the mesh will form, else results will come, else some it will throw up some error like deformation issues, like distortion issues it will show up. So you don't change this number. Okay, so while meshing I'm going to give the seed size as 5 e power minus 5. Okay, so why I'm giving that is you should get number of nodes less than 1000. So accordingly I chose that number. According to the 5 e power minus 5, you have to reduce your displacement or failure number, maybe 1 e power minus 5, 2 e power minus 5 you can give. So this 1 e power minus 5 works very good for you. So keep this number. Okay, I will come back to this point again. Okay, so going to your PDF again, we already gave JC material parameters, JC damage parameters we had given. Okay, so only yearly technique we have to apply. So yearly technique where we will apply, I will tell you in steps. Okay, so we are done with the mostly done with the material. Okay, so say okay. So now under materials you have aluminum. Okay, so but aluminum is assigned to tool or workpiece. We have not told the computer. Okay, so what in Abaqus we do it, we create something called section, and to this section we will assign the aluminum property, and then we assign the section to our workpiece. These three steps are important which we have to do it. Okay. Say for example, this is work. So we will create one section. To that section, we will assign aluminum property. Then that particular section will be assigned to this workpiece. That is how we will tell the computer this workpiece is made up of aluminum. Okay, there is a reason why this one more step comes into play. I don't want to talk right now. Maybe you will explore later, or we will talk about that later. Okay. So now you go and create section, work section. So obviously this is homogeneous only. It's not like hollow or something. Okay. So continue, and aluminum. Say okay to that. So you can go here in the right side and you can see the manager. Okay. I have created work section with solid homogeneous with aluminum properties. Dismiss and create this part. Assign. Select the regions to be assigned a section. So this is where I have to assign the section or material. Okay, you click this one and say done. So now set one is created. Make a note of it. Okay, we will use this one later. Done. So you assign work section. So this color will change to green. It means your material is assigned to this particular part. This should change to green, else it will throw up some error. Okay, so this is very important. Okay, so I'm done with my property. Okay, so part tool, I don't have to assign any material. So because this is rigid, if I'm modeling this one as deformable body, then I have to assign material property to that. Maybe like carbide properties, we can give it, create material, and we can give carbide properties, and then we create one more section, and then we can assign to this tool. So which we are not going to do it now. Okay. So 2D, we are taking this one as a rigid body. So let's go to the third step. So we have to assemble here your workpiece, and tool has to be assembled here. Okay, you go to the first one. It is saying create instances. Okay, create instance means it will copy the parts and put it here. Okay, so that any change in here will not affect our part, the original part, so that we can create many instances and do whatever we want. Okay, so let me create instance. Okay, I want to I want to include both tool and work, and whatever it is, click OK. Okay, so already your tool is inside your workpiece. I want it to move away. So very important in this step is we have to give your uncut chip thickness. You know, as highlighted by Sir, RTS is defined as ratio of uncut chip thickness to edge radius. Okay, so edge radius is already given, which is 60 microns. Suppose I have to keep the RTS as 1, then I should have the uncut chip thickness as 60 microns. So let's move the tool top, and I will tell you how to do that. So this is the tool which moves the instances. Okay, translate instant, choose your tool, click done. Okay, the lowest most point should touch this point. So now it is showing, is it okay? I am saying okay. See now you see it is like tool is touching on the surface. Now if you move the tool, it will be rub only. uh, so what is your uncut chip thickness right now, which is 0. Now I have to move the tool by 60 microns, so that my RTS is 1. Okay, if my RTS has to be 2, then I have to move this tool by 120 microns downwards. Okay, so before moving this tool downwards, I don't want the tool to touch right now, so I want it to move some way away from here arbitrarily. Okay, so let me move it. Okay, move this tool, done. You don't have to give any point, just whatever starting point, give 0, 0, enter. How much I want to move in the x direction? Maybe 60 microns. Shall we say 60 or 120 microns? Let me try with 60 microns. It is going up. Sorry, I given it the wrong direction. This is 60 microns, 0. 60 e power minus 6, 0. Then only it will move in the x direction. If you, yeah, enter, I gave it, but still it looks like if I go down, it will touch it. So let me give us, go back, 120 microns, 0. So first point I gave it as a 0, 0. Then this I gave some number, so that this tool will move by this much distance. Say enter. Now the tool has moved much far away, so this looks fine to me. So position of instance is okay to me. So let's click OK. Okay, still my uncut chip thickness is 0. Okay, so all I have to do is I move the tool by down uncut chip thickness. Okay, so let me do the RTS for 3. RTS for 3 means I take the radius as 60 microns. So I have to move the tool by 60 plus 60 plus 60, which is 180 microns. I have to do it. Okay, so let's move the instant here. Done. Starting point is 0, 0. In Y direction, I have to move 180 microns. Okay. Obviously, I have to move the tool not in the positive direction, in the negative direction. I have to move. So let me give 180 microns. Click enter. Okay. So this looks okay to me. Okay. If you are choosing RTS as 5, what you have to choose? 60 into 5. So 300 microns you have to move down. So I'm okay with RTS 3. So I'm saying okay to it. Now, what I have to give is I have to assign a velocity to this tool so that the tool will move like this. Okay. So let me save it for safety. Control yes. Okay, I saved it. Okay. So I'm done with my assembly. Okay. So what is the next step? Yeah, step. Okay. So before going to step in the assembly itself, you put a one point here. Okay. So which will be useful for us. If I have to move this tool, I have to apply my boundary condition to the whole tool, which is not necessary. So what I will do is I will create one point here and constrain the point to this tool such a way that once I apply my velocity to that particular node, it will move the whole tool. So for that, I have to put one point, okay, reference point. Click reference point and go here and put a reference point here. Tools, reference point, go and put a point here, okay. Then in the next steps, I will constrain it such a way that this RP1 and tool are constrained such a way that it will move together only. So this we will do it later. So the time being, you put this one, okay. You can come later and do it also, but fine. So go to step, okay. This is where we define our physics, okay. So you create your step here, step 1. So your physics is which one? Okay, that is we already gave material model. We have to tell what is the physics. Okay, it is a dynamic explicit problem. Okay, it is obviously the problem is dynamic and it is explicit problem because large deformation is involved. So we are not considering temperature the effect. So we don't have to choose this one. So dynamic explicit is enough for me to go ahead with that. So this will automatically tell what is the governing differential equation for the step. Okay, so continue. So I have to change this time period. Okay, say for example, this tool will move like this. Once it crosses, it will keep on moving it. So I don't want that to happen. So it has to stop at some point. So I want to run the simulation for a particular time only. That is according to the length of this one. So this is 2 mm, I think. If yeah, 2 mm we give. So according to the cutting velocity, how much tool has to run such a way that it will go and stop here. That I calculated